All right. Okay. So good afternoon, everyone. It is my pleasure to introduce Professor Wiberg today, presenting his work, his recent work. Let me tell you a little bit about him. He joined UC Santa Cruz after 29 years at UCLA as a professor and in electrical engineering and applied science department. And he joined here. He's done a lot of work since then. He's a lifetime member of IEEE, and a lifetime fellow of IEEE. It's a huge achievement. And today he will be talking about some of his recent work on identification and have connection with observers. And the title is, What is System Identification? How does it relate to estimation of system parameters? Thank you, Don.
Thank you very much, Ricardo. I really appreciate the invitation to talk before this wonderful group that you have assembled here. And Michael, thank you for you and your group's help in setting up this talk. It's a very nice way to get acquainted and to meet everyone. I am very anxious to help out in whatever way I can. I was just talking with my sister before I came here, and this was on FaceTime. She said, "Oh, hello, Captain Underpants," because at a Halloween party, I dressed up as this comic book character called Captain Underpants. So of course I had to reply, "Well, hello to you, General Pain in the Ass." So anyway, she told me I had to start out my talk with that. So this Captain Underpants is just following the General's orders, okay? Now, I wanted to say the reason I'm sitting on the table here rather than in the chair or hiding behind the lectern is that I like to be close to my audience when I talk and to find out when you are frowning at me. So please feel free to interrupt me at any time with any question, because if you don't do that, the people who don't feel like interrupting me but have the same question will not have an answer to whatever it is that's bothering you all. So just jump right in and say, blah, 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 you know, whatever it is that is not at all clear or wrong or whatever. And I'd rather talk to you than present my slides, okay? So let's just do it that way with that understanding. Just jump right in. Okay, so what about system identification? That's sort of what I've been interested in. And okay, the other one.
Yeah, there we go.
There we are. I thought I would say we're in a systems, cyber systems research institute. What do we mean mathematically? Well, we have to put this in and tell the computer what we're talking about. And that means, what do we mean by systems? Well, it's hardware or biological, political, financial, anything that's somehow, generally, maybe we can make a model, M, that can characterize a system and put it into language that a computer can understand. Well, besides the model, oops, besides the model, we need to collect data from the system and put that in a computer too. And often the math model is a set of input-output models, and they're parameterized by real numbers called parameters. And this best model from the set of models, see, this is a set of models. It's not just one model, a bunch of models. We need to find the best model, and we need to determine that. And then the best numerical values of the parameters of each model also have to be determined using the data. And therefore, we say, okay, well, what do we mean by the best? What is that? We have some criterion, C, that also have to tell the computer what is it that it needs. I'll get used to this in a minute, I'm sorry. Okay, so the mathematical statement that I've come up with is that given a model M and a metric C, let's take the data and adjust the model set such that C of D is best satisfied. And that's pretty abstract definition of the problem that I want to talk about. Let's be a little more concrete and do a really simple example to start out with least squares data fitting. And let's just take about the simplest. Let's say we know that y of t is the line described by a slope theta times x of t. And we get a bunch of data here that is a collection of capital N points that we could plot in the xy plane to try to fit theta. And let's choose the metric that's the sum of the squares of the errors of those points from that line. So here's the line theta xn, y minus the line point, that's the error, and it's the sum of errors squared. And therefore the best least squares model M is the criterion C minimized by the choice of theta. Okay, so that's a very simple least squares estimate problem, and we'd like to figure out how to do that. Another example might be machine learning. Now, I stole this slide that somehow got too far off the screen, off the web. And this is an advertisement called the Machine Learning Cheat Sheet. I'm not a machine learning or AI type person. I'm more of what I would call an old-fashioned guy, system identification guy. But I actually was able to recognize a few words on here like, oh, come on, Don, don't be so stupid. Let's see if I can't make the pointer work. Probability, how about singular value decomposition, linear regression, oh my gosh, gradient. Hey, what are you guys doing with my stuff? So it kind of looked familiar. All right, so that's a leap in complexity from a simple least squares problem to machine learning. And I claim the concept is analogous. Is it? I have to ask, you guys are the AI machine learning people. Is that fair to say it's kind of analogous to machine learning, to say you have something going on when you're having a machine learn something by adjusting models and parameters and other stuff in the machine learning? Is that okay? Anybody object to that? Well, nothing about machine learning. Okay, all right. Well, anyway, let's then say that there are, for such a construct, there are a whole number of considerations. I've had a lot of experience with system identification. I've done this for anesthesiology, for metal forming, for electronic circuits, for astronomy, for just a whole bunch of stuff. And I've seen a lot of dumb things done in the process when people have tried to actually do this. So I tried to make a list of considerations when you do something like this. If you have this model set, you want to balance complexity versus adequacy for the application. For example, it's not really good to have partial differential equations to try to solve those in the model each time around. They'll take an awfully long time to solve and that sort of stuff. It's very much too complex. But you can make it too simple, and then you lose the physical insight into what's going on in the problem. But you really need to use as much a priori knowledge as possible in choosing this model set. The choice of criterion is vital because the criterion choice can give almost any answer that's possible. And let me give you an example. Let's suppose I have a hypothesis that I would like to prove. And my criterion I'm going to choose, as perhaps some people have done in the past, simply to choose out of my data set all of those samples that agree with my hypothesis. Now, there is a hell of a good choice for a criterion for just giving any answer the statistician wants. Okay? So you can do this, and statisticians have done essentially this same idea in the past, is by choosing the criterion the right way, you can give pretty much any answer you want to. And therefore, you really have to say to yourself in doing this problem, what is natural? What is the most important way? And people really don't understand what it is that they want to do until they try to come and formulate this in mathematical terms. And if you can formulate the criterion in exactly how you want to do it, you're halfway there. That's the best way that I can say that this is absolutely vital. Choice of the data set. That is the experimental conditions. What has influenced the data? How can it be biased data? Are there ethical, safety, and legal questions in not only gathering the data, but using it? And you want to use as much data as practical. That's the wonderful thing about machine learning. Giant sets of data. And that data is the most important stuff that you've got to go on in trying to identify a system. So use as much of it as possible. And that's the big thing about artificial intelligence, is that computers can use giant amounts of data, and data is almost always more important than the algorithm. All right, choose the best model in the set. Each model is evaluated by this criterion in which the best parametric values are chosen for each model in the set. And you want to say, well, are physical laws violated? You want to incorporate that into the model. So that means that you have to choose the best parametric values in any model. And sometimes a parameter estimation algorithm is selected to find the best parameters using that criterion for each model. So what kind of an estimation algorithm do we want to choose? Will it converge to the true values? And we choose between algorithms such as in machine learning with large data sets, or maybe online algorithms such as filtering. And this choice is dependent upon how fast the answers are needed. And many times, the online algorithms can actually be used offline as part of a convergence criteria to use over and over to go into, then find the answer to a nonlinear problem. And that maybe is a way, such as just in smoothing. The Rostrom-Striebel algorithm goes once and then goes backwards to interpolate and so forth. So we don't want to dismiss online algorithms, even though the computer could do offline algorithms so very, very fast. Okay, so to help understand these parameter estimation in mathematical terms, let's do a quick study of the history of the problem. And it started out most popularly with Gauss. He entered it in his notes in 1794. And then in 1801, the astronomers were observing the asteroid Ceres. And Ceres was going in its elliptical orbit around the sun. And then, oh, it goes behind the sun. And the telescope, when it came back from behind the sun, they couldn't find it. And so, well, the orbit is an ellipse, right? So Gauss just says, okay, I'll fit an ellipse to least squares and find out if Ceres is actually the answer to that. And he says, look over here, boys, and they find it. So that says, okay, hey, least squares are cool. Well, actually, Gauss did not invent least squares. An astronomer named Coates published the least squares in 1722, 72 years before Gauss put it in his notes. And other people, Meyer and Lambert, all had a form of least squares before Gauss did. But what Gauss did was, first of all, he came up with the Gaussian probability density function. We even call it the normal density function now. It's so common. And the wonderful thing about that is under a linear transformation, it's still Gaussian. So we can keep track of it through a linear system just by keeping track of the variance in the mean of Gaussian. And this is the tremendously useful thing, and it led to all kinds of great things like Bayes and maximum likelihood and all that kind of good stuff. So that's, in my mind, the big contribution. Okay, next one. Well, now let's talk about an algorithm. Just as a nice example is this least squares thing. Given, let's suppose we have n data points. First, I'm going to do this non-recursively, that is offline. So let's start out with a really simple case where we have 2 points in the xy plane, and we want to find the best straight line starting at the origin, slope theta, that goes through those 2 points, okay? So what that means then is that we, according to least squares, we want to minimize S2, meaning I've got 2 points, the error y minus theta x1, that would be theta wherever x1 would lie on there, so that would be the error there. And then we sum the squares of these errors. And then we choose the slope theta to be theta hat. That's the best estimate of theta to minimize this criterion and zing, it goes right through between the 2 points, and we got a good estimate. And so theta 2 is actually the correlation between x and y divided by the variance of the x's. And there's another way of looking at this, is that theta 2 is in fact the mean of the conditional probability of theta given these 2 points. And we can look at, okay, then it's the maximum likelihood estimate of the variance of the error also. So that relates that to known statistics. Okay, now that was offline. Now we'll do the online solution. See, this says offline over there. Let's do it online. How does it relate to online? Well, come back here. I'm so sorry. I'm so... no, that's the wrong way. There we go. All right. So what this means is that the data arrives sequentially. So we get 0.1, 0.2, 0.3, and so forth. All, then we got to fit that line through. And let's start out then with just 1 point. Suppose we have just 1 point, we want to fit theta through the point x1, y1. Well, we take the derivative, set it equal to 0, and say, fine, okay, this expression here has to hold. And what that means is that the best estimate is just y1 divided by x1. It goes right through the point y1, x1. Well, previously, on the previous slide, when we had 2 points, we have this answer. That's the offline answer. Now let's put it into recursive form, all right? So we do a bunch of higgledy-jiggledy with the math, and eventually we come out with this. And now we recognize what this is, that theta 2 half y1 over x1. Oh, look, that's theta 1 half. So this is theta 1, the first estimate, given just 1 point, plus something times y2 minus x2, the new piece of data, times our original slope y1 over x1. That's theta 1. And in fact, then theta 2 is theta 1 half plus this k2, that's this stuff here, times what I call E2, that's the innovations. That's y2 minus y2 half. This is the best estimate. y2 hat is theta 1 half times the new point x2. So that we're incorporating the new data y2 and x2 here into this update to get theta half. And that's just based on what we knew before. And what that means is for any number of data, at nth point, we recursively compute that theta n is theta n minus 1 half plus some kn times this innovations n, where the epsilon n is yn minus the previous estimate for theta times xn. You can see that. I'm sorry. I'm sort of in the way here. But anyway, that's the whole idea. All right. Cool. Now, we can go. I wanted to do another example, a little more complicated. I wanted to relate this to Kalman Filter. So I wanted to do this other example that is, we have a differential equation here. Here's an input u going into a linear system that's autoregressive like this, and we'll call x1 equal to just z. That's this guy here in the differential equation with an nth order derivative. And we'll say x2 is its first derivative on to m minus first derivative of z that appears in this equation. And therefore, the last equation is this equation here, is that dxm dt, that's this guy here. So it's this mth derivative of z is theta 1 xm, that's this term. Did I do that right? No. Theta 1, or theta 1 xm, yeah, that's xm, theta 2 xm minus 1, and so forth, minus theta m x1 plus u. That's just another way of, all right. Here we go. That's just another way of writing this equation here. And what we've done then is we now have a bunch of first order derivatives for x1 through xm, like so, expressed in matrix form here. That's just collecting these equations here and throwing them into a form that MATLAB can deal with it. So that's just rewriting what I have up here for this system. I'm so sorry. I wish I was sane. Okay. So the point is, we can write any linear set of linear differential equations in matrix form. That's the first order form here, ax plus bu equals cx. And this can be done for multiple inputs. So let's put a vector sign there, and this becomes a matrix. This becomes a matrix. Any multiple input, multiple output. And in fact, A and B and C can all be time varying. And then, oh, we might add some white noise on here. And if we do that, then we get the least squares fit. So is that fun? Let's see if I can make this go the right way. Yes. All right. So now let's build a Kalman filter. What are we going to do with Kalman filter? Well, we have to define what kind of noise we're going to put on this system, okay? So let's define the VNs that are a sequence of random variables, statistically independent, zero mean, and jointly Gaussian. If we go to continuous time, then we have the derivative of a Wiener process. And if we have points y and xn, we let y equal f of xn plus vn. And then the least squares is just the minimum variance as to for theta hat, mean, conditional probability density, so that theta hat is the conditional mean and E is the expectation operator. And the nice thing about maximum likely is then we can get an estimate of the variance, okay, by maximizing the conditional probability. Oh, yay. All right, so what is the Kalman filter? The Kalman filter is then a linear state space representation of a differential equation in this form. It's actually something called Ito form, but that just means that this is white noise here and so forth. We describe white noise in the right way. And we can discretize this so that the computer can handle it. And then we just consider it at discrete time intervals, and that gives us a linear difference equation. And it's the same deal. Not a so wherever I have a differential here, just think also a difference equation, and we can throw it on MATLAB or whatever we want to do, okay? And now this is magic. Here we have, this represents a physical object, generally hardware or whatever we want, that's now could be a linear time varying differential, it could be a linearization of a bunch of nonlinear stuff, whatever. So it's multiple input, multiple output, and it has a bunch of noise on it. And that's what's generating our data points. So it's got process noise and measurement noise, all right? And we know what the variance of those are. We know that they're white. Okay? Well, now what happens? We take that output y. We know the input u, and we put them into this equation here, so that u and y are the Well, I shouldn't have a hat on. That should be just Y. I'm sorry. Erase that hat. It's just the input Y and the input U that we know that are going into the Kalman filter then. And maybe these A's and B's and even the variances are parameterized by a parameter theta. And again, it's the same form. Here is the state that we want to estimate, x hat, that's the output. The state estimate comes from the Kalman filter. And we pass the true output y, that thing off, minus y hat here. So we feed back the error through now a time varying gain, k of t. All right, so k of t has to be computed by another equation called the matrix-Riccati equation. It's of the same order, but it's n by n. This is an nth order state here. It's in terms of something that is a solution of the state error matrix. And so the Riccati equation that governs k is a function of this state error. It's independent of the state x at all times, but it does depend on the parameter stator in the form of A, B, Q, and R. But k of t is a time varying gain, and that was really Kalman's wonderful contribution, that Wiener came up with a constant k well before Kalman, but the good thing about the Kalman filter is it reacts much faster than the Wiener filter. And this, what does it do? Well, this equation here has noise on it. We don't know what x and y are in this one, okay? This gives the best minimum variance estimate for the state x. So we scrape the noise W and V off of this. This thing looks like the original equation, but with no noise on it. And therefore, all we're doing is we're making a copy of our physical system here, and we're updating it by stuff that is feeding back the measured point minus what we figure that point should be based on our past estimates. That's all the Kalman filter is. I want to point out that the Kalman filter can handle the case where the measurement noise is not white. It often happens that our physical system has colored noise in it. How do we handle that case? Well, if we can make a state space representation of V. See, this is the output of these prime variables here, V. Oh, that looks just like the Kalman filtering problem again, except it's for V. And we just extend the state vectors x and x prime, and we just write a new state space equation. And even though maybe this equation up here, our model, doesn't have process noise in it, if you have the coloration and you know what A is, in here, this is the transfer function to get you through to the coloration of the noise. If you know what that is, then you'll just have another Kalman filter, but that will have process noise in it due to the coloration. So you then, even though you think you might get away with something that doesn't have process noise in it, you might look at the case with no process noise and see if there's coloration. And then you can correct it via this way, and especially maybe you can, I'll give you a way to estimate what A prime is in the coloration. you can do that.
What is the change of coordinates?
I'm sorry?
What is the transformation that you do? What is the relationship between x prime and x?
You'll make a new state vector. I'm going to write parentheses here, and I put x here, and then I put x prime just below it. So it's an augmentation of the state vector. You start out with n, and maybe this has n prime states in it, so it's just an n plus n prime vector that you want to then put in, okay? And now you have a representation for the whole system, but with colored noise in it, right? But the Kalman filter needs to know A, B, C, maybe time varying, and also the noise variances and the values of any parameters in here. So, okay, we have to know what's going on a little bit more specifically. All right, so that leads to then parameter estimation. How do we tie? We don't know the parameters in a Kalman filter. How are we going to update these in a filtering form that is recursively also to help the Kalman filter? Well, there are two kinds of estimators. There is offline, that is not recursive, that's machine learning. And then there's online, recursive, like what I've just been talking about. You update things as the data comes in. And there are all kinds of offline estimators. There's a nice toolbox in MATLAB for the maximum likelihood stuff. But I like maximization expectation algorithm that's done with, there are lots of other singular value decompositions and all other offline stuff that is just wonderful, depends on the application. But the rest of the talk is pretty much going to be recursive estimations for which we can now build, here is the model has the output and the input coming into the Kalman filter here, but we don't know what theta is. Instead we have theta hat, and we just, oops, go back. Yeah, that was what I wanted. We just want to know then how to put a recursive parameter estimator so that we get theta hat into here to update those parametric values theta hat. Okay, so we're now going to talk about recursive parameter estimation. I especially like the book by Goodwin and Sen, published in '93. There's a Dover paperback for you cheapskates like me. Recursive algorithms in the early notes have a positivity constraint when you are especially doing the variance estimate, and that passivity constraint is due to the super-martingale approach, if you're familiar with that. However, if you apply averaging theory to the recursive filtering problem, it has no such constraint. And unfortunately, it can't guarantee convergence, and I want to talk about that. And for the remainder of the talk, I'm going to do a new parameter estimation algorithm. How am I doing on time, Michael?
You're doing fine. 4:41.
I got 20 minutes. I think I got it. Okay, so let's, I'm going to speed a little bit more. I'm going to do a new parameter estimate. They're not guaranteed to converge, but if they do converge, I've proven that it goes to a maximum of the likelihood function, and it's based on approximating the fourth order conditional moment of the optimal recursive parameter estimator that's expressed in the Kushner-Stratanovich optimal nonlinear filtering equation, And what we do is we take the formula for the Gaussian second order conditional moments, and then we replace the fourth order moment in the resulting probability density of this one, and we use averaging theory to prove convergence, assuming bounded estimates. And this approximation of the fourth order moment truncates the moment, so you only have to consider first, second, and third order conditional moments. The assumptions of this thing are 9 in order, and I think I'll just skip this slide. You can look at them later. It's a bunch of technical shtick. Properties, it's in state space form, recursive like the Kalman filter. It looks like the extended Kalman filter parameter estimator, where you just say, well, I'll tell you in just a minute, I'll do an example, but it's not. This permits the extended Kalman filter parameter estimator to work with unknown process noise or colored measurement noise, like I was telling you about. It's asymptotically equal to, within a change of variables, to the state space form of the recursive prediction error method of Leonard Jung and his folks. It's based on optimal nonlinear filtering, that is the Kushner-Sutanovich equation of continuous time. It's the exact equations of the first, second, and third order conditional moments, and these moments determine the stability of the new estimator. It's a Gaussian approximation of the fourth order conditional moment of the nonlinear filter, and it truncates the higher conditional order moments. They go away because, in fact, each higher moment just depends on the moment previous, one order lower than it. So therefore, if you have this fourth order moment that is expressed in terms of the sum of second order moments, then you don't need to do the fifth order moment, which only depends on the fourth order moment, and so forth. So you just get rid of them. And I proved that this, if it does has bounded estimates, it converges globally with probability 1 to a minimum of the maximum likelihood, maximum of the maximum likelihood, maximum of the likelihood function. And it converges to the true parameter values, not parameter, if in fact we have just one output and that generalization of the minimum phase condition. And the big advantage of this thing is that it converges quickly for parameters in the state matrix, not for the ones in the process matrix. That's still got to go like 1 over t, but it converges exponentially like a Kalman filter for those parameters. And I'll give you an example of that. And the drawback of all of this wonderful sounding stuff here, I hope, is that the parameter estimates have to remain stable. We don't know that. It's not guaranteed by averaging. So to show you what I'm talking about, I'm going to do a simple example. The simple example is we have just a first order system with an unknown time constant tau, all right? And this is the Laplace transfer function. We've got a white noise zero mean going into it, but we don't know the variance. I call the variance rho. We're going to have to estimate rho and tau. And then we have a white noise, and let's say we know the parameter. It just, turns out it doesn't matter what it is. You can say it's known, but it doesn't matter. And then we get a parameter estimator, and out comes tau hat and rho hat. That's the parameters we want to estimate there. So the spectrum of the output is R, and I guess there should be a delta function there, and omega, and then rho, and then it goes through this, the white noise going through that filter, so it's got that phase spectrum. And then in state space form, it's exactly what you would think it is. There's the filter, and W has variance rho. Okay. So now we're going to first take a look at the extended Kalman filter parameter estimator. And what that does is say, okay, here we have the Kalman filter for the state, and this should be a tau half, although it should be halves on these, and rho half. And it turns out that this d rho dt equals 0 and 0, and you can't do it via extended Kalman filtering for this problem. It turns out that this has no solution, but let's do it anyway. Extended Kalman filtering, that means that we take our f of xc here, which is this state vector x tau p, and this is f of xc. Here is its Taylor series, so it's its derivative, it's minus tau and minus x of this. That's a partial with respect to x, and this is partial with respect to tau, and then everything else is 0, of course. You take derivatives of that guy. And what this means is that the extended Kalman filter parameter estimator is dxc half. This vector half here is f of xc, that you plug it back into this guy here, plus the solution of the Riccati equation times the error update here. And the extended state error variance obeys this Riccati equation here, where this is now the linearization of this f here, that's partial f partial xc. And it just depends upon the q of rho over r, and so we could just take r equals 1 in this case. Okay, so now instead of solving those matrix equations, let's just write out each one separately. And therefore, we have, for the extended state xc, we've got 3 equations. That's these here for the extended state. This is the Kalman filter. And we've got 6 equations. 5? Wait a minute, come on. Oh, okay, there's another one down here for the error. Well, anyway, why is it 5? Let's see, now, this is a 3 by 3 matrix. 1, 2, 3, 4, 5, 6 in that. I should have 6. Pi. No. Anyway. I think I'm missing one down here. All right. So, what's the new algorithm look like? Where we're going to add on this third order moments. How do we change those equations on the previous slide, which are the extended Kalman filter, that doesn't work because we don't know what the variance is? Well, we omit that part of the p equation. It's often makes a thing converge better if we add a third order moment in tau and a third order moment in rho. This is the thing that the extended Kalman filter doesn't know. M of rho is the expected value of rho tilde x tilde squared. It's the third order conditional moment of parameter x transpose. That's the key. We can add that to the extended Kalman filter. This thing will converge. And it'll converge even faster if we keep track of the third order moment with respect to tau. So that's what's going on. And let's investigate what does this really mean. So I took that simple example and actually computed the variances and everything went through. The pain of actually coming up with a state plane of, oh, crikey, with a state plane of tau hat and rho hat. And we need to interpret the phase plane or state plane of rho tau parameter estimates for that particular example. And how do we interpret it? Well, let's look and see the slope of d tau hat d rho. If that slope is big, then the convergence rate is much faster than rho over tau. And what that means is this inverses that slope is big, then d rho d tau is about 0, means it's flat in the state same plot, and d tau d rho is big. So it means we get fast convergence then along flat lines in the state plane convergence. And convergence rate is much faster than 1 over t. All right, so here it is. 3 cases. I've plotted the state plane of the convergence of tau and rho to the true parameter values in the center, and I do that for the case now here where the true parameters are 1 and 1/8, 1 and 1, and 1 and 8. So where it converges to, it's always converging to the center points of these things here, which are the true parameter values. And let's look. They all look the same, pretty much. And out here, it's flat. What does that mean? That it converges exponentially to this line. To that line there. And then what happens? Well, let's follow it in. Now it goes, and this is essentially the biased least squares value, where we don't know what the parameter variance is, and then it converges like 1 over t to the true parameter variance. So the example then says, hey, my new parameter, it indicates, I haven't proved that, but it indicates that the new parameter estimation algorithm converges exponentially in the parameters of the system A matrix, and like 1 over t to the parameters in the variance matrix. Okay, the trouble with that nice sounding new parameter estimation is that we have to augment the parameter vector to the state vector. In other words, put the x primes on here, like theta primes. And we say if theta, the ith parameter theta, is constant, that means that d theta I dt is 0. That puts a pole at the origin for each parameter. And it's well known in feedback, 3 poles in the origin, you just can't do it. Damn it, I can't stabilize this thing if there are 3 parameters and it's really bad. Well, the idea then is, okay, let's simply add more sensors to that problem. Now we could say for each sensor we could have this very fast exponential convergence of the system parameters theta. There's only 1 or 2 poles at the origin, and in fact Jet Propulsion Labs since the 1960s has been using in fact the extended Kalman filter, and they just guess the variance parameter, and they estimate parameters in the orbits. And they use many sensors. So that means that actually people have really known all this stuff anyway. It's not any big news, it just puts it in more mathematics. So the extended Kalman filter and the new algorithm can quickly estimate variances recursively and can be used in many applications. So my conclusions for this talk are: parameter estimation is part of machine learning. It depends upon the criterion selected. This parameter estimation can be done offline or recursively, and recursive estimation gives quicker response. And hey, wait a minute, computers are really, really, really fast. Why do we need to even bother with recursive system identification? Well, it turns out there are a few actual practical influences where you do want to do this. I mentioned one of them as part of it, doing a nonlinear thing, searching at linear, or that sort of stuff, as well as this. But what I'm getting to is the bottom point there is that machine learning can incorporate recursive algorithms to increase the speed of response, especially in the case of fault detection. In fault detection, you use a hypothesis test when you know the variances. So you have to compute the variances, and that's what this algorithm does. And then the hypothesis test of whether a system is working or against the hypothesis that there is a fault in the system that you model, and then you can pick that up with a hypothesis test. And that will then be a way of attacking the fault detection problem. So I want to conclude with, I have been studying the new parameter estimation algorithm for the past 7 years. It's in fact led to an exciting and possibly lucrative application that is patented by UCSC. I haven't mentioned or showed you that. I have no money now to finance students, but indeed I welcome cooperation, especially since I have spare time as an emeritus professor, with anybody who's interested in this new area of research. So that is, thank you.
Thank you very much for the very nice presentation.
Uh-oh. Yeah, you.
So, Tom, thanks for the talk. The British statistician George Box once said, all models are wrong, but some of them are useful.
I didn't understand.
There is a statistician.
Yeah, I know, Box.
George
Box Jenkins and all that.
Once he said, all models are wrong,
yes.
Some of them are useful.
Yes.
Can you comment on that?
Oh, definitely. I completely agree. You have to find the useful one. This is the art of engineering. And finding an appropriate model is very difficult. And you'll know it because the data will tell you it doesn't. You get the wrong answers. So you have to test things out. You have to go kill a few people. And perhaps that's what the driving people had to find out. And I have a suggestion to them that people should know that this is dangerous. To start with any test, it is dangerous. And you have to start with a small community and tell people there that they will be recompensed for anything that goes wrong, and let them know honestly what's going on. And then maybe you can talk to other communities around and do it like a multi-grid search. Then you put it to cities, and eventually you get the whole state to accept it based on data, and then maybe you could get eventually the federal government to mandate that this is an okay thing. But otherwise, bridges fall down, people get hurt, and we don't want that. We have to be very, very careful. And that's why power companies are so damn hard to sell. There's so much money involved with a new power plant.
Thank you.
Yeah.
Small question. Why you couldn't prove exponential convergence in the example?
Why couldn't I?
Yeah. You told us that you couldn't prove exponential.
Because I have to find an expression for the rate of convergence. And I couldn't. I simply couldn't. Would you like to do it? I'd love to have somebody help me out here. I think it's true, but I'd like to have somebody work on that. I'm too old. I get too confused.
It's linear, no?
What?
It's linear.
Yeah, you'd think it would be easy to prove, but I broke my pencil. Thank you. Nice question. No, I'd love to have somebody look at that one, amongst other ones. Working on this. All right, I'll have to. The project I've been working on is with Professor Pedrati, and this is essentially the next level up from that simple example. We're just working on a harmonic oscillator, and you have to find for a harmonic oscillator, you have an input sine wave, and you want to find the amplitude and phase. That's a Kalman filter if you know the frequency, but to estimate the frequency, that's a parameter. So this is a parameter estimation problem now in two-dimensional state space plus one parameter. So it's three-dimensional extended Kalman filter. And people have been looking at this. Well, I first ran into this problem in the textbook by Brian Anderson and John Moore on Kalman filtering. It's an example in there. That was published in early 70s at least. So that's been around a long time. Bob Bitmead and his student Barbara LaScala and other people like James and so forth have been looking at this, and the Italians, Vitante and Savarese and so forth, have also looked at this thing. I have been able to characterize the solution to that much better than they have.
For the general algorithm that you proposed, you had a slide with a bunch of assumptions. You said that the most difficult one is to keep the trajectory on the set.
Yes. Yeah. To prove that the estimates are bounded, because averaging theory must make that assumption.
So you're working on bounded sets in general?
Well, in general, you don't know. You can't really prove it. You can build that into the algorithm, but who knows whether the algorithm is any good then. I don't think it's any good then. It just slows it down. You get shattering at the boundaries and so forth. So if you incorporate into the algorithm a passivity constraint on the update of the variance especially, then Goodwin and Sin's book proves convergence of such an algorithm. It's a slightly different thing. But you could look at the book and see what they did. And of course, it's done at discrete time. Everybody's afraid to look at the Kalman filter in the continuous time, but since I have people listening to me that sort of understand what I'm talking about, there is no optimal nonlinear filter in discrete time. No equation like the Kushner-Katanovich equation. You must go to continuous time, to the Ito form. And if you think about that, it makes sense. That, okay, we have to discretize the continuous stuff. To put it on the computer, everybody's solving the Riccati equation on the computer in discrete time. But continuous time gives you a better, simpler understanding of what's going on in the whole filtering problem to begin with. Because there, again, is no innovations, really, expression in discrete time. I mean, you can express it, but it's not optimal. It's not a cushion cut out. There is no optimal nonlinear filter equation.
Then I have another question. Your algorithm is estimating the state of a model from the output.
And the input. You have to know the input.
But you don't know the state either of the system.
No,
So
no.
you're doing two things at the same time.
Yes.
Is there any benefit when you relax that and you just worry about the estimation of the parameter only?
How do you do it? Well, you have to keep track. You have to keep track of what's going on. And if you're going to keep exact mathematical track of what is going on, you need to know the differential equations.
Yeah, no. I'm saying you remove the estimation problem of the state.
Okay.
You just focus on.
I see where you're going.
You focus on the parameters.
You could go into the frequency domain and maybe look at it that way. Still, you're stuck with keeping track of the process as it comes in. To do it exactly, I think. Maybe not. Maybe there are ways around it.
Anyone waiting for? No. Okay, any other questions?
Well, thank you for a wonderful discussion. I appreciate everybody's attention. Very nice. I hope we can all have the conversation in the future with each one of you. Come by and just have a beer.